So, hello everyone. Myself Sujit Sapuda. We are group number 5. Today we are going to present the topic is temperature dependent properties of tin bismuth based low temperature solder based alloy. Next slide, please. So the problem statement is like as the packaging uh, uh, the domain is expanding and the node size is becoming more lesser and lesser, and the components are becoming critical due to miniaturization. So traditional soldering temperature methods, which uses like 220 degrees centigrade, is not friendly for those devices. So we are proceeding for next generation soldering techniques and the alloys. So one of the alloys, the previously we are using like a SAG, that is a tin silver copper based alloy. But as you can see in the figure, the at the 240 degrees centigrade, there is a lot of garbage issue is there. So the uh, as you can see, the tin lead based eclectic solder based alloy, which have a lower melting point like 183 degrees centigrade, it cannot be used due to the environmental concern, as the lead is carcinogenic, and the tin bismuth is offering low temperature, um, that is 138 degrees centigrade, but has a reliability limitation due to its lower wettability formation of the intermetallic compound. So, next slide, please. So, current technical status. First of all, this tin tin bismuth composition which we are using in the microsystem domain, there are majorly three varieties. First is eutectic tin bismuth based alloy, which have melting point of 138 degrees centigrade. So this is a standard for the temperature sensitive package due to its laminar structure. The alternating silicon, tin rich phase and the bismuth rich rich phase. Second is a tin bismuth silver system. So due to the addition of the silver into this tin bismuth, the it is improving the mechanical properties like tensile strength. As you can see in the graph, the due to the on the x-axis you can see the tin bismuth and the Ag addition have improved the tensile strength uh, compared to the tin bismuth based alloy. Third is a tin bismuth indium based alloy. So addition of the indium have reduced the melting point to the ultra sensitive component. On the left side, you can see the graph of the um, tin bismuth alloy composition. At the 57% of the bismuth, it is the eclectic point. So yeah, for the next part, I am handing over to the Srinivas. Yeah, thank you.
So, myself Srinivas, and coming to the properties of the tin bismuth based alloys, its thermal conductivity is generally has a lower thermal conductivity, that is 21.6 watt per meter Kelvin, which is less than half of the tin lead based alloys. So due to this lower thermal conductivity, so these alloys have some heat dissipation issues. And this thermal conductivity can be increased by allowing addition. So as here we can see that by adding silver to 0.4 per mole fraction, we can increase the thermal conductivity by 13%. And tin bismuth based solder alloys have lower wettability. Here wettability refers to the ability of the solder material to adhere to the substrate and to form a good joint compared to the traditional solder alloys. So this lower wettability is due to the higher surface tension of bismuth and the oxidation tendency of the bismuth to form bismuth oxide. Coming to the question of thermal expansion, so this tin bismuth based alloys have a lower, have a coefficient of thermal expansion of 16.7 ppm per degree centigrade, which is like comparable to the CTA of the common substrate materials of copper, like copper and FR4, which whose coefficient of thermal expansion is about 14 to 18 ppm per degree centigrade. Because we are having a good match of coefficient of thermal expansion, we can reduce warpage of the substrate. But these tin bismuth-based solder rails have lower creep resistance. This lower creep resistance is due to the higher homologous temperatures. That means like higher working temperatures. If we can see, the general operating temperatures of this microsystems packaging is around like 80 to 90 degrees centigrade, and the melting temperature is around like 188 degrees for this tin bismuth-based alloys. So as we're working in hot working conditions, then it can accelerate the creep deformation. And in the right side in this graph, we can see that it has a lower thermal fatigue resistance compared to the traditional tin, silver, and copper-based alloys. Here, the x-axis represents the number of thermal shock cycles, and the y-axis represents the maximum shear load to failure. So here, what I've done is they have took 3 samples: tin lead, tin silver, and tin bismuth-based alloys. They have subjected it to the thermal shock cycles between the 25 and to 125 degrees centigrade. By varying the thermal cycles, they have calculated the maximum shear load to failure by doing shear tests. Here, as we can see, for a thin bismuth-based alloy, as the thermal shock cycles increase, the maximum shear load decreases, which can be due to the formation of voids, which can decrease the effective cross-sectional area. So one of the main existing issues with the tin bismuth-based alloys is that is the formation of intermetallic compound. So the intermetallic compounds that are formed are eta phase Cu6SN5 phase, and which is growing at the solder side, and epsilon phase, which is Cu3SN at the copper side. So these phases are formed due to the formation of Br-rich phase near the interface due to aging. So depleting the interface region of bismuth, so leading to only copper and tin interface. At elevated temperature, these reactions would happen frequently. Like the chances are high that these reactions can occur. And generally, the intermediate compounds are brittle in nature, which can adversely affect the mechanical properties. So in the right side, we can see that as there is an increase in temperature, the mean thickness of this intermetallic layer is increasing. Basically, we are increasing the kinetics of this reaction by increasing temperature. So I'm now handing it over to Mustafa. Thank you.
So, hi everyone, myself Mustafa, and I'm explaining this slide of the another existing issue is the electromigration. Electromigration phenomena. What is the electromigration phenomena? Is the movement of the metal atom under the high current density leads to the reliability issue in tin bismuth solder joints. The atomic migration and the phase separation. The tin atoms migrate faster than bismuth atom. So it's leading to the bismuth atom accumulation of the bismuth atom at the anode and the tin rich region at the cathode. The below picture is showing the separation of the accumulation and the accumulation on the other side of the bismuth and accumulation of the tin rich region at the cathode. So this is due to the unequal the atomic diffusion. At the time of the electromigration, tin and bismuth atoms diffuses at different rates due to the difference in the atomic size and the bonding energy. Typically, tin atoms diffuses faster than the bismuth atoms because of the atomic size difference under the electric current. So the vacancy accumulation is the faster moving tin atom leaves behind the vacancies. If these vacancies do not get filled by the slower moving bismuth atom, they merges and they form the cricketall voids. Then the defects formation, void, cracks, and bismuth vickers develop due to the atomic flux divergence affecting the mechanical and the electrical properties. Impact of the reliability leads to the increased resistance due to the high localized high resistivity of bismuth. Localized heating will be happen, and it will leads to the potential open circuit and the void formation and crack propagation that leads to the early failure in electronic packaging. Can you go to the next slide? Okay. So the future trends are development of the novel alloy composites for tin, bismuth, X. That is X is the zinc, nickel, and silver system to improve the wettability. Wettability increases means the spreading area of the joints increases. The left side graph shows that the at the zero composition the spreading area is low, but as we increase the alloy composition, then the overall wetting area is increases. Though titanium reduces, but the overall spreading area increases. Addition of the ceramic based nanoparticle that improves the mechanical properties, and the due to the addition of the graphene, it will improve the thermal conductivity. So the composite solder particles and the tin bismuth core surrounded by the higher melting of the SiC 305 alloy shells provide a novel approach to balancing the processing temperature with the reliability. The right one graph is showing that if we reduces the interface spacing, then the material strength will be increases. That's all. And further slide will be explained by the Survi. So
So continuing with the future trends, tin bismuth solder paste are used as a thermal interface material for power electronics, and when bond line thickness is minimum, achievable thermal resistance is less than 5 millimeter square Kelvin per watt. And to measure the thermal resistance, we have two methods: laser flash techniques and scanning acoustic microscopy SAM. Thermal resistance also decreases after 300 thermal cycles, that is from minus 45 degrees Celsius to 125 degrees Celsius, which improves reliability. It is also suitable for power module attachment, which offers low cost and a large scale processing benefits. So coming on to conclusions, what we have discussed till now in the presentation. First of all, it has a low melting point advantage. Tin bismuth solders has a melting point of 138 degrees Celsius, which offers a crucial processing temperature reduction compared to traditional solders, which enables the assembly of temperature sensitive components in microsystem. And balancing properties, by solving temperature challenges, tin bismuth solders present trade-offs in thermal conductivity, wettability, reliability that requires a careful consideration in design. It has some key challenges. For example, formation of the brittle intermetallic components such as Cu6SN5 and Cu3SN, and poor electromigration resistance and thermal fatigue concerns remains significant challenges for the same. It has some promising enhancement strategies by addition of some minor elements such as Ag, zinc, and nickel, indium, and some ceramic nanoparticles or some composites improves reliability and shows the potential for addressing inherent limitations. As emerging applications, thermal interface materials for power electronics, flexible electronics, and thermal sensitive microsystems represent growing opportunity for tin bismuth solder implementations. We also have some future outlooks for tin bismuth solders. Combined approach is leveraging compositional optimization, microstructural engineering, and a system level design will be critical for expanding tin bismuth solder adoption in advanced microsystem packaging. That's it. Thank you.